All right, and this one, 54, the density of nitrogen of 0.913 atmospheres in 18 degrees C is 1.07 grams per liter. Explain how this shows that the formula of nitrogen is N2 rather than just N. And so this particular problem, from the density, we can go ahead and calculate the molar mass. The molar mass using the equation that we had earlier, and then just compare the molar mass. So this is the equation for the molar mass. The molar mass is equal to MRT over PV. The mass over volume is the density, so it's equal to density times R times T divided by P. So we just plug that in here, and then we get a molar mass of 28.0 grams per mole. A molar mass of 28.0, that means there's got to be two nitrogens rather than one nitrogen, because if there's just one nitrogen, it gives us a molar mass of 14. 0 grams per mole. Okay, let's see. At a given temperature and pressure, what mathematical relationship exists between the density and the molar mass? Well, this is it. The mathematical relationship between density and molar mass. The molar mass is equal to the density times RT over P, with the mass over volume ratio of okay. And so here they're deriving the particular equation. Anyway, we're going to need the pressure and the temperature. So it's molar mass times P over T. It's the density. So we looked at those equations earlier. Labels have become detached from cylinders of two gases, one of which is known to be propane, the other butane. The densities of the two gases are compared at the same temperature and pressure. The density of gas A is 1.37 grams per liter, and the density of gas B is higher. Which one should have a higher density, the propane or the butane? Well, which molecule weighs more? Butane weighs more, so butane's going to have a higher density. You're going to get the same number of gas particles in a volume. It's just going to weigh more. So gas A has got to be propane, gas B has got to be butane. Butane's heavier. They calculated it, but we don't have to necessarily calculate. An organic chemist has produced a solid that she believes to be pure. She expects a molar mass of 346 grams per mole. Using 4.08 grams of the solid, she melts and then boils it in a 3.36 liter vacuum chamber at 117 torr and 253 degrees C. She is disappointed. The molar mass is close to what she expected, but not close enough. What molar mass did she find? Okay, so the molar mass, this is what she was hoping to get, 346. We can figure out the molar mass. The molar mass is equal to the mass over the moles. So in other words, grams per mole. And so what we can do is we can just get the equation for the molar mass and then plug in the values there and then calculate the molar mass. So what molar mass did she find? We calculated using the equation. Molar mass is equal to MRT over PV. Plug in the numbers, 334 grams per mole. Yeah, that's quite a bit different there. 334 versus 346, which was what was expected. Her findings suggested to her that what her mistake might have been. Does it suggest anything to you? Part B. Her molar mass came out lower than expected. Why could that be? Well, let's just see. The answer. This is beyond discovery. The difference between the expected molar mass and the molar mass that was found experimentally is 12 grams per mole. This is the atomic mass of carbon. Perhaps she has one too many carbon atoms in her expected mole. I don't know. I don't know about that. Can't sit there, but it's a proposal. All right, those are our all the questions in chapter 14. Just skipped a lot of the stoichiometry since they were very similar. Now, what we're going to look at next is chapter 15. So, let's bring up the PowerPoint for chapter 15. Now, chapter 15 deals with gases, liquids, and solids. And so what I'm going to do is I'm going to cover this. I'm not going to use the PowerPoint for this one. I'm just going to cover it. Oops, what did I do on the pen? By just board lecture here, because that'll be a lot more compact. So what you should study is just what I talked about in class here. And so what we're going to do is we're going to talk about solids, liquids, and gases. Well, we already talked about gases, so we're not really going to talk much more about that, except it's going to be incorporated in here. Solids, liquids, and gases. So typically, if we have a solid, all the particles are packed together in some kind of, what do we call this kind of structure? A solid. Like a lattice. It's packed together in some kind of lattice like this, crystalline lattice or amorphous lattice. And then if we heat it, this is the symbol for heat, what happens to the solid? It melts. It melts at some temperature called the melting point. Then we form a liquid. When we look at a liquid, what's the difference between a solid and a liquid?
There's translational.
Yeah, there's translational. So now something got translational, but all the particles are still being held together. And then if we continue to heat it, we'll form a gas in which the particles are all spread apart like that. So, what holds the particles together in a solid? And so, this is why I'm not going to go in the order of the book. What I want to do is I just want to talk about solids first. And solids are discussed at the end of this chapter. So I'm going to talk about it here. The solids. We have two types of solids. We have crystalline solids and we have amorphous solids. The difference between a crystalline solid, which is up here, and amorphous solid, which is down here, is both of these should be blue. The crystalline solid has a very well-ordered pattern, whereas amorphous solids don't. They lack that ordered pattern. And so, here are some examples. Polyethylene would be more of an amorphous because it's not, although you see order in there, short range order we don't see long range order. But, short range order is definitely present here. Whereas over here, these will show long range order as well. So this is crystalline silicon. This is crystalline aluminum. This is crystalline sodium chloride. This polyethylene bottle is made up of amorphous, somewhat amorphous chains. These are very, very big molecules, these chains. They don't have a fixed length. They can go longer or shorter depending on how long you make those chains. Some of the properties are between crystalline. Crystalline, because of this order, if you see this is called cleavage. It cleaves very nicely. Whereas amorphous, it fractures in a colloidal pattern. Colloidal pattern because we don't see cleavage planes up there. So amorphous solids, they say, do not break in predictable patterns, whereas crystalline solids would break into predictable patterns like this. So like diamond for tables. So this structural impact there. Now, this is types of both amorphous and crystalline solids. This should just be types of solids. Types of solids. The solids are going to be characterized by what holds the particles together in a solid. What holds the particles together in a solid could be ionic bonds. If ionic bonds are holding the particles together, we call them ionic solid or ionic lattice. Whether it's crystalline or amorphous, this makes it sound it has to be crystalline. We have covalent solids. What holds covalent solids together or covalent lattices together? Covalent bonds. And we have metallic solids. What holds metallic solids together? Metallic bonds. And so those are the chemical bonds. You know, these are the forces that hold the particles together. So in a solid like this, either bonds hold it, and we have three types of bonds. We have ionic, covalent, and metallic. Or we have something called an IMF. An IMF is called an intermolecular force. Intermolecular force. Intermolecular forces are weaker than bonds. And what intermolecular forces are these electrical attractions. These are also electrical attractions, but these are quite a bit stronger. So these are weaker electrical attractions than the bonds are. Weaker electrical attractions. So ionic bonds are strong. These are strong electrostatic forces. So you got to think, you know, how strong? Well, in order to melt it, we have to break apart the forces that hold it together so that they can translate. And so ionic crystals or ionic solids, easy to melt or hard to melt? Have you ever tried to melt table salt? Easy to melt or hard to melt? Maybe you've never tried to melt it. It's hard to melt. Stuff is hard to melt. In fact, I tried to melt it on the stovetop. It wouldn't melt. It doesn't get hot enough. It's got hot salt. And so ionic bonds are strong. They're the forces that hold positive ions and negative ions together. Covalent solids. Covalent solids are held together by covalent bonds. For example, diamond. Diamond has tetrahedral carbons. You know, if you look at it, and they're all held together by covalent bonds. Are diamonds easy to melt? No, very hard to melt. And so ionic solids and covalent solids have high melting point. They have strong bonds. It also means that things like diamond and quartz. Diamond and quartz are held together by covalent bonds. Diamond and quartz are very hard materials. They're hard materials because the bonds are very strong. However, salt, is table salt a really hard material? No, table salt is a brittle material. And so it's very like okay, so let's look at ionic would be like salt. And salt is, you know, high melting point, which means strong bonds. However, it's brittle. And the reason it's brittle is because of this. You have a positive ion being attracted to a negative ion.
like this. Now what happens if you push this down? If you push this column of ions down, what happens is you get negative and negative. So we'll bring this down, and then you get negative, negative, and positive, positive, and it just splits apart like that. And so that's what's happening here. What's happening here is he's pushing down a column of ions. As he's pushing it down, the positive, and the negative and negative are now aligned because they're offset. You know, they're supposed to be positive, negative. But if it goes negative, negative, and positive, positive, then they're offset one row and they split apart. So this whole layer will come off. That's called cleavage.
Cleavage. And so that causes them to be somewhat brittle. Ionic solids, these are typically soluble in water. Because water is what we call polar, very polar, and water likes these charged ions, water being polar, unless the bonds are too strong. So the ionic bonds become too strong with like the phosphates, the carbonates. The higher the charge, the stronger the bond. So those tend to be insoluble. So they're typically soluble. And so ionic solids are hard to melt. But when you do melt them, what happens? When you do melt an ionic solid, you know, the lattice is now more mobile, right? Now we have translational motion. And so the situation is the ions are still held together. The ions are not flying apart. And so when we do melt it, the ions are still held together, so we get a molten salt. In a molten salt, what holds the ions together? In a molten salt, what holds the ions together are IMFs. IMFs are called intermolecular, but they don't have to be between molecules. Inter just means between. In the case for molten salt like this is a solid. When we go to molten, what holds the molten salt together are what we call ion-ion attractions. And so this would be the liquid. And so we've broken, you know, the bulk of the bond, but the ions are still held together. These are held together by IMFs, or intermolecular forces. IMFs is kind of incorrect because there are no molecules here. These are just ions, but they're held together by ion-ion attractions. But these ion attractions are not so strong that we call it an ionic bond. An ionic bond are ion-ion attractions, but it's quite a bit stronger. Does that make sense? No, it doesn't make sense? Okay. So what happens here is this. When we have a solid here, that means the bonds, or IMFs, are stronger than the temperature. That is, the temperature is a measure of what? Temperature is a measure of kinetic energy. Kinetic energy. And so the kinetic energy is not enough to break the bonds, so everything stays together. What happens in the liquid are that the bonds / IMFs are about equal to the kinetic energy, KE, the temperature. And so in this sense, the kinetic energy and the bonds are about comparable, so now they're able to move. They have this mobility to them. Now, if we take this molten salt and continue to heat it, what are we going to do? We're going to break the ion-ion attractions holding the ions together, and then the ions are going to go vaporize into the gaseous state where the kinetic energy is greater. And so in this case, the bonds / IMFs are weaker than the kinetic energy, you know, the temperature. And so here, the ions are going to be split apart. They're no longer going to be held together. So that's what we got for this.
Think about water. Well, actually, let's go on to the next one here. The next one would be like a covalent solid. The covalent solid, an example of that would be diamond or quartz. These are two covalent solids, diamond and quartz. What holds together a covalent solid? Covalent bonds. So when we look at the bonds, like in diamond, for example, diamond's going to be tetrahedral carbons, all arranged like this. We're going to see a nicely ordered lattice of tetrahedral carbon atoms. And so diamond has a very high melting point, and it's very hard. Is diamond and quartz soluble in water? These tend to be insoluble. Insoluble. If we were to melt diamond, what do we have to break? We have to break all these covalent bonds. It's not so easy. And so if we had molten diamond, we'd have carbon atoms moving around. If we have carbon atoms moving around, then what are they held together by? They're held together by IMFs. But the IMFs would be different. You know, if we had molten carbon, these are ion-ion attractions. So of course there's going to be an attraction between positive and negative. But carbon atoms, are they ions? No, carbon atoms are going to be neutral. And so if we had molten diamond, all these bonds would be broken and the carbon atoms would be mobile. But what holds the carbon atoms together in the liquid? What holds the carbon atoms together in the liquid are IMFs. But the IMFs are going to be different in this case. The IMFs are what we call London or dispersion forces. These are also known as AKA instantaneous dipole. Instantaneous induced dipole. And so if I have two carbon atoms, what in the heck can hold them together? You know, what type of electrical attraction can hold them together? And so it's easy to see between two ions, you know, ion-ion. But if I have liquid carbon, you know, then something's got to be holding them together. And what holds them together is this. How many electrons does carbon have? We have a nucleus here. Let's look at a carbon atom. You have a nucleus there, and then how many electrons does carbon have? 6 electrons. Now normally those 6 electrons are evenly distributed in the electron cloud, the first shell, the second shell, right? They're going to be evenly distributed. But what can happen is, can you pinpoint the electrons? Are we able to pinpoint the electrons? No, we can't pinpoint. Why can't we pinpoint the electron? Because of what principle? I mean, with the Heisenberg uncertainty principle, good. And so what can happen is this. We got 6 electrons, and let's say all 6 electrons decide to be on the left side. Or actually, let's put 1, 2, 3, 4, 5, and then 1 on the right side. Well, all of a sudden, the electrons are on the left side, more so on the left side than on the right side. what's going to happen is we're going to get negative charge build up on the left and positive charge build up on the right. But that's not sustainable. Pretty soon things will spread out. This is like a wave, you know. And pretty soon, in a pool, there's a wave in a pool, and eventually it's going to spread out evenly. That wave was just a instantaneous disturbance on the surface of the pool, right? Well, the same thing here. We got this little wave here, and there's an instantaneous disturbance in this electron cloud distribution such that there's more electron density on the left than on the right. Is that going to stay that way forever? No. And so what we have is this is called an instantaneous dipole. Instantaneous dipole only lasts for an instant, and then it's gone. Is the wave going to stay there in the pool forever? Somebody jumps in and causes a wave. Does that wave stay there forever? No. Eventually it's going to disappear, but in that moment when the wave is there, then something can happen, right? And so the same thing here. In this moment that we have an instantaneous dipole here, that's going to induce a dipole in the next carbon atom. And so if I have another carbon atom over here, what's this carbon atom going to see? This carbon atom is going to see there's more positive charge here. And so what's that going to do? It's going to pull the electrons to the left. You know, the electrons are going to see the positive charge here, and they're going to migrate to the left side of here. And so what that's going to do is it's going to induce a dipole over here. And so the electrons move. To this side, and we induce a dipole here. This is called an induced dipole. And so for one moment, when that wave is there, for one moment, there's an attraction. And that attraction, the attraction is called a instantaneous induced dipole attraction. My other pen. Or, that's kind of a long way of saying it. Okay. So that attraction I'm going to write is some dots here. This is called a London dispersion force, or London force. There's three names for it: London force, dispersion force, instantaneous induced dipole. They're all three of those refer to the exact same thing. And so I can call it any one of those I want. And so I'm just going to call it London force. There's going to be a London force. How long is that London force going to live for? As long as that wave's there, and then it disappears, right? The thing is that these electrons are always moving, so the next wave is going to appear in the next instant. And so what we have is we have a net attraction, net electrical attraction between nonpolar species. And so these are the only attraction between nonpolar species. Instantaneous induced dipole, London dispersion force. That's what's going to hold the carbon atoms together. Okay, then if I continue to heat it, then I got to break these. You know, if I get gaseous carbon atoms, I got to break those, and then the carbon atoms are free to vaporize into the gaseous state. Does that make sense? Not at all? What part of it doesn't make sense, you say? The atom itself has no dipole. The atom itself is neutral. It's just a carbon atom.
So what is the dipole?
The dipole is when a carbon atom has 6 electrons. And so it's when the electrons aren't frozen in space. The electrons move. If more electrons just by chance move to the left side than the right side, then the charge is not evenly distributed. When the charge is not evenly distributed, we generate a dipole with uneven charge. And so that's, but you know, normally it's evenly distributed because everything's all spread out in the orbitals, in the shells, right? And so it's all spread out evenly. And so this dipole only lasts an instant of time. Normally a swimming pool surface is flat. But if somebody jumps in, there's going to be waves. Do those waves stay there forever? No. But in that instant, there are waves. And the same thing here. Normally, this is evenly distributed, but in one instant, the electrons all decided to move to the left side. They don't think, but I mean, maybe, I don't know. They just move to the left side, causing a disturbance. It's no longer even. That's what we call an instantaneous dipole. That it lasts long enough to attract the atoms and hold them together. Otherwise, there's nothing to hold the atoms together. You know, gravity won't hold it together. Some people think, oh, the atoms weigh. No, the atoms weigh nothing. You know, for example, how much does a single water molecule weigh? Does a single water molecule weigh more than a piece of dust or less than a piece of dust? A single water molecule is so small you can't even see it. A piece of dust you can see. So a piece of dust is actually massive, huge compared to a single water molecule. But if I blow on a dust pile here, what's going to happen? The dust pile is going to disperse into the room. But if I blow on a water molecule, a whole bunch of them, do all the water molecules disperse into the room like a dust cloud? No. And so something very strong is holding the water molecules together. We'll talk about that in a minute. But anyway, this is it. Now, metallic solids are the next type of solid that we have. In metallic solids, what is the force that holds the metal atoms together? Metallic bonds. Now, metallic bonds can range from very weak to very strong. You know, and so the melting point, there's going to be high melting point for some and to very low, depending on how strong the bond is. So some things have a pretty low melting point, like potassium. Potassium's melting point's pretty low, versus some things have a very high melting point, like platinum or tungsten or gold. Those have very high because the bonds are a lot stronger. And so metallic bonds range from weak to strong. These are pretty much not soluble, insoluble. Metals are, but will react with oxidizers. You know, you could get metals to dissolve with oxidizers, and then you can get the metal to dissolve. But you know, you have to oxidize it. It just doesn't dissolve. If you try to dissolve a piece of lead in water, it's not going to dissolve. But if you try to dissolve a piece of lead in an oxidizer, it'll dissolve like nitric acid. Lead will dissolve in nitric acid. And so the metallic bonds hold these. Metallic bonds, as you call, is like, you know, where we have the metal ions and the sea of electrons, you know. And so it's like this, metal ion with a sea of electrons. The sea of electrons is delocalized over the lattice. Okay. So when we melt this, we get mobile metal atoms, and when we melt this, we're breaking the metallic bond. And so what's holding the metal atoms together? Well, when we melt it, what holds the metal atoms together? Well, metal atoms are like carbon atoms. They're neutral. They aren't ions. They aren't ions, so dispersion forces hold the metal atoms together in the liquid. Now, if we continue to heat it, we can break those dispersion forces and get the gaseous metal, you know, vaporize the metal. And so that's metallic. And so far we did ionic, covalent, metallic. These are held together by bonds. Bonds. Molecular crystals are held together only by IMFs. And so let's take a look at molecular crystals next. IMFs. Now, there are different types of IMFs that we can look at. Let's rank them from weak The weakest IMFs are going to be the London. This is a ranking based on equal size. Equal size molecules. So typically the weakest are London forces. There are other names for London. What are the other names for London? Instantaneous, induced dipole, and one more, dispersion. And so the weakest are London, and then the next one is, these are instantaneous dipole. Then comes dipole. These will have a permanent dipole. Something that has a permanent dipole would be like, let's see, what would be a good one to do? Like HCl. HCl has a permanent dipole, chlorine's more electronegative. Whereas something like this, instantaneous dipole, would be like CO2. CO2, this is nonpolar. There's no positive and no negative. I mean, essentially it's nonpolar. So what holds two nonpolar ones together are going to be London forces. What holds two HCl's together will be dipole. And so HCl will be held together to another HCl by, let's do it a different color here. We'll do it green. So the forces that hold these two molecules together will be dipole. So I could have solid HCl. Normally HCl is a gas. Normally, room temperature HCl is a gas, which tells me that these are weak. These have got to be weak. They've got to be so easy to break. CO2 normally is a what? CO2 is normally a gas. That means the forces holding CO2 molecules have got to be really weak. Because the temperature, room temperature, the kinetic energy of room temperature is enough to break them completely apart. And so CO2s, these are the weakest. The only way we can get these to liquefy and solidify is to cool down the temperature. When we cool down the temperature, we can get these to liquefy and solidify. And so we go weakest, London, to dipole, to something called H bonds. H bonds are an unusually strong dipole. Unusually strong dipole. And this only happens when if H is bonded to an oxygen. If H is bonded to an oxygen, we get a big dipole. Or H is bonded to a nitrogen, we get a big dipole. Or H is bonded to a fluorine, we get a big dipole. And so when H is bonded to oxygen, nitrogen, or fluorine, we get a big dipole. Fluorine would be the biggest, then followed by oxygen, then followed by nitrogen. And so, for example, water. Is water a gas at room temperature? Or is water a liquid or a solid at room temperature? It's a liquid. That means the forces have got to be a lot stronger holding them together, correct? And so the forces are a lot stronger that holds them together. What are the forces that hold them together? The forces that hold water molecules together are H bonds. Oh, I can't do it this way. H bonds. So the negative end of the water is attracted to the positive end of another water. And so, you know, water is a liquid, so it's stronger. And then there are others. The others